All right, here we are ready to start Chapter 4, Nuclear Chemistry. Particularly exciting chapter in my mind. Hopefully you'll agree. If you don't now, by the end of the chapter, I hope you will, because it explains a lot of the nuclear phenomenon that we experience in everyday life, and a lot of it's based on, again, that nuclear stability that we touch on just a bit in this course. If you go on to a physics course or nuclear physics, modern physics type course, or radiochemistry course, then you're going to talk about that a lot more. We tend to be more concerned with the electrons, but we'll spend chapter 4 here thinking about that nucleus. So in the first section of this chapter, we're going to look at natural radioactivity. So we're exposed all the time to natural radioactivity, just naturally occurring radioisotopes, things like uranium, for instance, in concrete. There's not a whole lot of it, and there's not a whole lot of background radiation that we experience because of it, but it's enough. It's something we should think about and something we should talk about, and here we have an opportunity in Chapter 4 to think about natural radioactivity. In thinking about radioactive isotopes, let's go ahead and define those. If you remember, an isotope is just a particular mass of a given element, where isotopes vary based on that mass number because of a difference in neutrons. Sometimes we have an unstable nucleus, and this typically happens with the heavier elements, usually things above atomic number 20, although certainly carbon-14 is an example of a relatively light atom that has, at least in the carbon-14 isotope, radioactivity that's pretty important for radioactive dating and things like that. Radioactive isotopes emit radiation to become more stable. They change. This is sort of the idea of the alchemist trying to turn lead into gold. Well, here we really typically do see a change in element identity. Carbon-14, for instance, transmutates into nitrogen-14 as part of its decay process. Radioactive isotopes can be one or more of the isotopes of an element. Typically, elements have at least one stable isotope, although that's not always true. And if we look at the human-made elements there in the lanthanide and actinide series, we have cases where there are no stable isotopes. They're all radioactive, and they just have different degrees of radioactive decay based on how fast the particular isotopes decay. A radioactive isotope is identified by writing the mass number after the element symbol. So we could say iodine-131 by spelling out the word, or we could just have the symbol I-131. And so here we have the following symbol, the symbol of the element, the mass number, which is the number of protons and neutrons for that particular isotope, and then finally the atomic number, the number of protons. Obviously, if we have the symbol of the element, then we know that for iodine, for instance, it has to have 53 protons. That's why in our iodine-131 or I-131 notation, we don't bother to talk about the protons. If we give the complete symbol with the superscript to the left having the mass number and the subscript to the left having the atomic number just before the element symbol, then we do tend to include the atomic number just as a reminder of the total number of protons for that element. Okay, so here in table 4.1 we see a list of some stable and radioactive isotopes of some elements. So for magnesium, for instance, we have the stable isotope magnesium-24. For radioactive isotopes, magnesium-23 and magnesium-27 are radioactive. So there's something special about that nucleus in magnesium-24, and what's common, as you'll see in other examples that we'll hit, we have 12 protons and 12 neutrons in that stable magnesium-24 isotope. Having, first of all, an even number of neutrons tends to be a very good thing. And here we have an even number of protons as well. In the case of magnesium-23 and magnesium-27, there we still have that even number of protons, 12 protons in any isotope of magnesium, but we have an odd number of neutrons, 11 neutrons in the case of magnesium-23, 15 neutrons in the case of magnesium-27, and it's similar to chemical stability where there are certain magic numbers. We use the term loosely. Of course, there's no such thing as magic in science, but we call them magic numbers because they give special stability. If we look at iodine, iodine 127 is our stable isotope, and in that case, we do actually see we have 124 neutrons. Iodine 125 and iodine 131, well, actually, those both have stable number of neutrons as well, but they don't give a stable nucleus. So it's interesting. We don't get into enough of the nuclear chemistry or the nuclear physics to talk about why some isotopes have a stable layout and why some don't. We just sort of take it for granted that if I tell you it's radioactive, you understand the nucleus is not as stable as if I tell you it's a non-radioactive isotope. Finally, uranium has no stable isotopes. They're all radioactive. In a couple examples, U-235 and U-238. U-235 is the more desirable one. That's the fissile form. U-238 is fissionable, but it's a more difficult process. Okay, so when we say radioactive, we're not always talking about the same type of radiation that's emitted. So radiation is energy emitted by that unstable atom as it tries to move to a more stable state. So the key types of radiation we'll tend to talk about in this course are alpha particles, which are basically helium nuclei. So the helium, most stable isotope of helium, helium-4, which has 2 protons and 2 neutrons, and we have no electrons around it. So it's an ionized form of helium. Beta particles are really high energy electrons, so they have a charge of -1, just like an electron should, and they have a mass number of 0. Again, not because the electron has no mass, but because it's relatively small, and when we're just looking at mass numbers, we don't take into account that very, very small mass. We treat it as 0, although we understand electrons or beta particles do have mass, and it's just a very, very small mass. The other types of radiation that we'll focus on in our course, the positron, which is like a beta particle, except it has an opposite charge. So it's like a positive electron. Therefore, it has a mass similar to the mass of an electron, a very small value, but we have, again, assumed it to be 0 for our purposes here. And we see that's the process that generates that positron is a proton converting to a neutron. So it's losing its positive charge part while retaining most of its mass, and that's how we emit a positron. And then finally, gamma rays. These are actually the easiest ones to deal with. So they're high energy radiation. They're typically associated with other types of radioactive decay as well, but the gamma ray itself is just really high energy electromagnetic radiation, really short wavelength form of light that it's not light we can see as visible light, but it's light energy, and therefore it has no mass and no change in atomic number. So it's not even a particle, it's a wave of high energy light. Okay, and here we see table 4.2 to summarize those different forms of radiation. So the alpha particle is either the Greek alpha for its symbol or the helium nucleus symbol for the mass number 2 for the atomic number, and then the helium symbol He, capital H, lowercase e. And so it has a mass number of 4 and a charge of 2+ from those 2 protons. A beta particle has either the Greek beta or 0 superscript, -1 subscript, and then lowercase e to denote an electron. And that has a mass number of 0, although it is a particle with some mass. It's so small compared to the mass of, say, an alpha particle that we just assume it to be 0. Its charge, being an electron, is -1. And the way that we get that is by having a neutron change to a proton. So the neutron loses its negative charge that's been balancing out that proton's positive charge and converts to a proton. Positron has either the beta symbol with a superscript plus after it to remind us it's not an electron but rather a positron, or the 0 superscript +1 subscript followed by a lowercase e. And again, we said that happens when a proton changes to a neutron. So if a neutron changes to a proton, we get a beta particle. If a proton changes to a neutron, we get a positron. Finally, the gamma ray is the Greek gamma, either with or without the superscript subscript 0 set there. and that's just energy loss to stabilize the nucleus. So the nucleus is metastable. It has a little extra energy. If it can emit that, it can relax into a stable nucleus. Being a form of electromagnetic radiation, it has a mass of 0 and a charge of 0. And finally, a proton, just as a reminder, we have that symbol lowercase p or 1,1H, and that's because the protium form of hydrogen, that isotope of hydrogen that has a mass of 1, has just a single proton. So a proton's emitted. That does happen from time to time, although it's not as common as the other types of radiation we'll discuss. And the mass number will be 1, and the charge, obviously, +1. Finally, a neutron emitted. More commonly, the neutron's actually captured. But in any event, the neutron itself has as its symbol lowercase n, either with or without that superscript 1, subscript 0 to indicate its mass and charge number. So if a neutron is emitted or absorbed, we could show that neutron as part of that nuclear reaction, mass number 1, charge of 0. Okay, so why do we care so much about radiation? Well, probably the most important reason we care about radiation is there are biological effects of radiation. When radiation strikes molecules, electrons may be knocked away, forming unstable ions. And so this is a problem for our cells, especially if they're bombarded with lots and lots of radiation. That can cause so much damage that the cell will die. Almost as bad, although worse in the long term if it propagates, would be a cell that's damaged in its DNA. So you get a mutation in that cell, and then it might start dividing uncontrollably, such as cancer. So radiation can give rise to either cell death or damaged cells that ultimately can become cancer cells and cause death of the organism later on. If the ionizing radiation passes through the human body, it can interact with water molecules. We're mostly water by mass, so we can make these H2O plus ions, and those can cause chemical reactions. They're scavenging for electrons to get back to neutral water, and if they steal electrons from the wrong species, as I said, that can result in either cell damage or cell death. And ultimately, if this happens enough, and if it generates cancer cells that propagate, ultimately death of the organism. Okay, so I told you we're bathed in radiation, naturally occurring radiation. Now I tell you that radiation can cause cancer and kill cells and kill humans. Well, this can put your mind at ease a little bit, because the most common type of radiation that we encounter is alpha and beta particle decay. And so paper, a single sheet of paper or a layer of clothing is more than sufficient to stop alpha particles. They're big, but they don't have very good penetrating power as a result. For beta particles, which are smaller, they can penetrate a little better, but a lab coat, gloves, those are just enough to stop the beta particles. If you get into gamma, which fortunately we don't experience a whole lot in terms of natural background radiation, you'd need a lead shield or thick concrete wall for gamma rays. Gamma rays are used in certain types of cancer treatments because they are very effective at killing cells, as long as they're focused on the cancer cells as opposed to the healthy cells. So what should you do to protect yourself? Well, you should limit the time spent near a radioactive source or increase your distance from the source, especially those alpha particles. They don't have good penetrating power, so if you're far enough, and in that case just a few feet away from the alpha source is typically enough. You also have to be careful about how you're exposed. Radon, which is a problem in the bedrock in Pennsylvania and the southern tier of New York, and we have to be cautious of that. And if you're going to spend a lot of time in your basement, you should have it tested, or the lowest level of your home tested for radon, because that's an alpha emitter, but it emits from inside. You breathe it in, it's a gas, a noble gas, and then it has access to those healthy lung cells, and it can cause lung cancer as a result. If the alpha decays from outside, like the uranium and the rocks and concrete and all of that, it doesn't have much of a chance to penetrate. But if that alpha emitter can get inside, like in the case of radon, then it does have a chance to damage healthy cells and unfortunately result in lung cancers if it's long-term exposure that's not checked. Alright, so here we have table 4.3, which talks about the properties of ionizing radiation and shielding required. So alpha particles, they can only travel 2 to 4 centimeters on average, so they can't get very far into tissue, 0.05 millimeters. So basically the dead layers of skin are all that the alpha particles can interact with. For shielding, a single piece of paper, light clothing is plenty to stop those. A typical source here we have is radium-226. For beta particles, they can penetrate quite a bit better, travel further, penetrate deeper. So there you need some heavier clothing, lab coat, gloves if you're working with beta emitters. Again, we have beta emitters in our body right now. Carbon-14 is not a very prevalent isotope of carbon, but it is part of the naturally occurring carbon. So we do have some of that going on all the time, but it's relatively small and it doesn't do a whole lot of damage. Finally, gamma rays, they can travel quite a distance, 500 meters. They can penetrate very well, also 50 centimeters or more. So you need really heavy-duty shielding, lead or thick concrete, and technetium-99M, that M denotes it's a metastable nucleus and it's a gamma emitter, is a typical source. That's used in medicine. As I said, sometimes we want gamma rays for cancer treatments or other reasons. And so it's important that we be able to make them where we need to, but also protect ourselves from them if we're not using them for a specific purpose. Okay, so let's, before we end this first part of Chapter 4, let's do a couple learning checks, see how we're doing with these concepts. So for the first learning check, what shielding is required to protect from the following forms of radiation? So for alpha radiation, just jot down what that would require, and then gamma radiation, what type of shielding would that require to protect you from that form of radiation? Go ahead, pause the video if you need, or we'll see how you did. Alright, and for the alpha radiation, remember that's the big helium nucleus that's really massive but not very good at penetrating, so just a thin sheet of paper or a thin layer of clothing is plenty for protection from alpha decay. If we look at the gamma radiation, that's quite a bit more penetrating, and therefore you need a lead shield or a really thick concrete barrier in order to protect yourself from the gamma. So not only do we care about the type of radiation, we also care about where it's able to interact. The alpha, as I said, is mostly harmless from outside, but if it gets inside our lungs through radioactive radon, then it can do quite a bit of damage. Gamma can do its damage anywhere that's not protected by that heavy-duty lead or concrete protection. Alright, and here for our final learning check, which form of radiation emitted has a mass number of 0 and a positive charge? So if you could list its name and symbol, one of the acceptable symbols for that particular type of radiation. Go ahead, pause things now, or we'll go and see how you did. Okay, that which is described in this particular learning check is a positron. So that's shown either as a beta, Greek letter beta with a plus superscript after it, or 0 superscript plus 1 subscript followed by a lowercase e to denote that it's an anti-electron. It's an electron in terms of being a particle about the mass of an electron's mass, but it has a +1 charge as opposed to the -1 charge. And as we see here, it comes from a proton in the nucleus decaying into a neutron and emitting the positron outside. Hopefully this first part of Chapter 4 has been interesting and hopefully not too challenging for you, but if you are struggling, certainly please review these core concepts, check some end of chapter questions, check the homework set questions, and get in touch with me if things still aren't making sense.